So in this lecture, we are going to learn about the topic that is called self-weight. So, so when a member is freely suspended, like in this condition, um, so this is the fixed part, and here the member is mounted here at the fixed part. So a member is freely suspended, fixed at the top, and the in this condition the axial load is applied by its self weight. So let me write the whole thing. When a member is freely suspended which is fixed at the top, the axial load in this condition, the axial load is applied by itself. It is applied by its self weight. Now suppose we have to find out a stress at x location due to its self weight, then how we can find? So just consider the x section. This is the x section, and we have to find out the stress at any x location. So the first thing we have to find out is the sigma x at any x location. So the weight will act something like this here. Yeah, this is the self weight acting downwards. So we can write P is equal to P of x, because the load is, because the axial load due to self weight is depending upon the distance from the x section, that is x point. So we can write sigma x is equal to px upon ax, which is the weight of the other side. Px, we have already studied that in order to calculate the axial load, so we can calculate the load at either side. So px is the weight of either side divided by the area. So here we know that the density is equal to mass upon volume. So so px generally can be calculated by the equation mg. That is the self weight. Px is the self weight, that is mg. So in order to calculate the value of m, so we are going to use this equation. So we can write again, that is the mass is equal to density into volume. Here we can write m as m equal to rho dot volume is a dot x, that is the area of this rod upon the x distance. So we can so px, so we can write px is equal to rho dot a dot x multiplied by g. So sigma x we can write as sigma x, the value of px is rho dot a dot x dot g divided by the area. So a gets cancelled out, and so what we are left with is the rho gx. So for calculating the self weight, we can use this equation, that is sigma x is equal to rho gx. So this is the equation for calculating the stress during self weight condition. Now moving forward, let's see how the stress is varied in this section. So basically, let me erase this thing first. Yeah. So what is the stress distribution during this self-weight condition? So just imagine that um, let me erase this thing. It will be better to give an overview. Okay. So just imagine that um, there is a hook and or a rope attached to this hook, and one person is hanging. Um, one person is hanging by catching this rope attached to the hook. Now so when due to the gravity, the hook will be subjected to some stress of due to the weight of the man. So let's another man is hanging by catching the leg of another man, this man. So the stress will be increasing by the hook when the another person is attached. Similarly, when another person is attached, so the value of stress again increases at this point. So we can call it as a people hanging concept. People hanging concept. Okay. So similarly, the value of stress distribution will look something like this thing. So here there will be maximum stress distribution. At this point there will be maximum stress distribution, maximum stress distribution, and the value of stress then goes on decreasing. Then it becomes like this thing. This is the distribution when we move from top to bottom approach. And here it will be the minimum, here it will be minimum stress, here it will be minimum stress distribution.
Got the man with the plan right here.
So we can see that stress distribution will be uniform but the stress intensity varies. Now the other question can arise that what is the change in length due to the self-weight condition? So mm, so delta L is equal to the integration of 0 to L sigma x dot dx divided by the Young's modulus. So this is the condition for when the like any quantity is varying for okay. So we can write sigma x as 0 to L rho g x dx rho g x dot dx divided by E. Now after further solving we are going to get del L is equal to rho g upon E x square by 2 0 to L. Now out of further solving we are going to get the value of delta L. So delta L will be equal to rho g L square by 2E. So you can see that delta L due to self weight does not depend on area. Cool. So we can further simplify this equation by taking area up and down, that is rho g L square A upon 2EA. So we can, after further simplifying, we can write it as WL upon 2EA. So in this condition also, delta L is not function of area. Oh, okay. So this was all about this lecture. So in the next lecture we'll be discussing about the component of varying like distribution of stress in varying cross section with some numerical. So for now, thank you.